Laser welding is much more environmentally friendly than traditional forms of welding. It uses less energy, it causes less environmental contamination, and it can trim a lot of processing steps, and so it can save time and money in the end.
It's inherently a very difficult system to study, and industry really doesn't have the time. They're busy creating products and getting them out into the world.
One of the goals of the project is that we want to be able to make a tool that will assist people in welding new things. So if you're a company and you have a process where you want to weld two different metals, a lot of times you don't know where to start, and you could spend a lot of time and energy in doing that sort of proof of concept work.
What we're embarking on here is quantitative analysis to be able to provide a weld prediction database to industry so they don't have to start at square one. They can immediately get a set of conditions and a set of parameters.
The materials that you want to weld, how thick they are, what they're made out of, what kind of laser you have.
So they can be welding right away and not have to experiment for days or weeks or months in order to find the proper weld condition.
So the process of welding, you put two materials together. You apply the energy, in this case laser energy, and the energy actually melts both pieces of material. And once that material solidifies, that material is known as the weld bead.
So a weld bead is what you're left with after the welding process is finished. So it's what ends up being your mechanical joint between two different pieces of metal. In this case, we just created a single weld bead on plate in the shape of the NIST logo.
So this booth here is a computer-controlled laser welding booth. And we use this as a test bed now to develop measurement techniques for the laser welding industry. We have a high-power fiber laser on this side of the room, and that laser light is coupled into a fiber optic cable. 10,000 watts of optical power from the laser are transmitted through the fiber that goes across over the ceiling and down into the weld cell and goes into the weld head where the optics are to focus that light down onto the weld sample. And that could be steel or aluminum or other types of materials as well. And at a fraction of the maximum power that these lasers operate at, it melts bricks into glass. So that gives you a sort of a tangible idea of what high power lasers really are capable of doing and why we need accurate measurement of them in order to apply that to an industrial process.
When you're welding with a laser, the big thing that you care about is how much light am I using. In some applications, to get a quality weld, you need to know the laser power to within plus or minus 1%. Problem is, when you're welding, it would be very nice if you could measure the laser power at the same time as you're welding. And because this technique absorbs all the laser light, you have an option. You either weld or you measure the laser power, but you can't do both. Light is made up of photons, and in this example you could think of photons as being like this tennis ball. They travel along, they have momentum, and the tennis ball comes at a certain velocity, bounces off the racket, and goes the other direction about the same velocity, but the racket recoils back. You feel a force from the tennis ball turning around, from its momentum changing. Well, it's the same way with light. The photons travel, and instead of the racket, suppose you have a mirror, light will come and reflect off the mirror, but it also pushes on the mirror when it reflects. So our idea is, what if we measure the power in a laser by measuring how much that laser pushes on a mirror? So how do we measure that? You can use just a commercial scale. Have the body of the scale and you have a little balance pan that you put your mass on to weigh it. But instead, let's replace this pan with a mirror. Here we have a fiber laser that puts out about 500 watts. The light's going to come and go through the first window, reflect off our mirror, which is attached to the scale, and it'll measure the force of the light. It'll exit the second mirror, and it'll come over here to this traditional thermal power meter. The light that's coming out of the fiber collimator here is turning on and off, on and off. So here on the monitor, what you see is a region where there's no force and there's no reading from the scale, and then the light turns on and it shoots up and you see a force. That force is proportional to the laser power.
Welding is an inherently violent process, and when the energy hits and melts this material, some of that material will actually vaporize.
So in this case, we're set up to do a sample weld on a steel pipe here. So the plume is pretty much in the area where the light hits the test sample. So in this case, right about where my finger points. And we have a couple different optical tools to monitor the weld process. So with this system here, we can collect the light that's coming out of the laser weld plume and send it to spectrometers that can spectrally resolve that light. Spectrometer gets you a certain amount of sensitivity, but to look for those really hard to see elements that play a large part in determining the strength of your steel alloy, what we can do is we can deliver a second laser light pulse that we can tune very accurately to specifically pick out these lighter elements.
Once we've created a weld in the laboratory, we then want to analyze it in our precision imaging facility, where we have a number of advanced tools that allow us to explore the microstructure of the material all the way down to the atomic scale.
So in this lab, I take pieces of the welds that are made in the other building and I section them and make very small specimens to look at in this transmission electron microscope. And this uses a high energy beam of electrons to interact with a sample, and it gives off all different kinds of signals, and we use many of these signals to learn about what's in there. In fiber laser welding, the welds are very small and the laser power is very high, and so we get very fast heating and cooling rates. What we want to understand in this project is how those cooling rates affect the final weld that you get. It turns out that in almost all materials, actually, the precise placement of the atoms can affect the macro scale properties that you and I can observe with our eyes. So here's an example of a weld that we made in our fiber laser welding booth in the other building. There's a couple things that you can see here. One is that there's a pore in this sample that's about 70 nanometers in diameter. It's very small. You can't resolve something that small with your eye, but it can still actually have an effect on the mechanical properties. Cracks can form around pores and then they will break the material.
Then we have a comprehensive mechanical testing laboratory where we'll perform fatigue and fracture experiments to understand that relationship between material properties and structure and allow us to predict the performance of the weld in the field.
So in this lab, we use test machines to basically pull materials apart and learn their mechanical limits. This is the lab where we break things. This is a tensile specimen. You can see the weld at the center line. And what we do, we actually pull this apart, and as we pull, we measure the force that it takes to pull this apart. So we pull on the specimen, it stretches in the machine. This can take anywhere from a few minutes to a few hours. During the test, you'll typically see what's called necking in the specimen. Basically what happens is this thing stretches, it starts to thin in the middle, and once it starts thinning, all the stress localizes at that thinned place. And that's where the breaking will occur.
You wouldn't find a world-class group of laser metrologists and a world-class group of material scientists this close together in really any other organization in the world. And that's what makes our program uniquely beneficial to U.S. industry. Because of the way we're structured and organized, we can take these problems on and really do a deep dive. I'm expecting in the next 3 to 5 years we'll have some really well-developed tools to deliver to industry and to be able to help them with this process.